Welcome to Patterns for the Cloud. It's, well done to everyone for finding the session. I noticed that it disappeared off the website yesterday, and I thought that was actually a pretty good sign, given that when I asked about it, they said that the website was absolutely not broken, but instead the website was eventually consistent, which is basically the whole point of this talk. So decided to take that as a good omen. I'm James. I work for a company called Intergen out of Wellington. I'm their practice lead for their North American Modern Apps group. So we do a whole bunch of work with Microsoft and a couple of other large corporates in the States. Prior to that, I worked for Microsoft as a developer. So for the last 10 years or so, I've been doing interesting things with that data and finding opportunities to break Azure. And that's kind of where this talk came from. I'm really excited to be here talking about this particular topic because last year I got to talk about building web apps at scale, and we talked about patterns around CDN and websites and a whole bunch of other technologies. But when it came to the data tier, I kind of had to wave my hands quite a bit because that's really the hardest part of building applications at scale in a public cloud environment. So this year I'm back and we're going to tackle the really hard questions about how do we do data at scale in the cloud. So what are we going to talk about today? We're going to briefly touch on why data is interesting, if you're not already convinced, and why doing this in the cloud is hard. We're going to talk about what I think, in my opinion, is the minimal data pattern that you want to look at when you're building apps in the cloud. We're then going to talk about a concept of scale-free, that is, how do we break some of those traditional scale restrictions of relational data stores. Then we're going to talk about going beyond relational data and talk about some NoSQL options and where they make sense. We're also going to talk about just a little bit of big data, just a very small amount of it. And then finally, we're going to be talking about how we build our apps to survive. So at the end of today's session, you should have a pretty broad overview of the entire Azure Data Platform. This is a pretty ambitious scope for a 1-hour talk. So if I skip over your favorite topic too quickly, please raise your hand and we can do questions as we go. Right, so why is data interesting? Before we get to why is data hard, let's talk about why is data interesting. So first off, the amount of data is going to explode over the next 5 years. EMC forecasts around 44 zettabytes by 2020. That's a really big number, and it's a 10-fold increase of where we are today. While a lot of this data is coming from new and modern streams like IoT and social and mobile, and a lot of this will actually be, in fact, created by consumers, the vast majority of it will be managed by enterprises, somewhere upwards of 85%. So that means if you're sitting in this room, chances are this data explosion is going to be your problem. The only thing that really is in our favor is that the cost of data storage has just plummeted. And I think most people at this point would have seen the comparisons between modern data storage costs and that of data storage costs back in the early 80s, where it was something like $400,000 for a gigabyte of storage, and now it's somewhere in the vicinity of 3 cents. And while that's all very interesting, and yes, we can definitely say that storage has become cheaper, what I think is really interesting is what's happened just on Azure, where it's dropped within 5 years from 15 cents to as low as 2 cents for a gigabyte for a month. And the same story goes for compute. So we have more data, we have somewhere great to put it, which is nice and cheap, and that's a really good thing because one of the most expensive things you can do with data is to try and recreate a data set that you've lost or deleted in a rush to free up disk space. So if we have all this data, it's really cheap to store. Where's the opportunity? Where's the chance for us to improve our business? And the key to this is our ability to go and pull in different types of data. So this is no longer a discussion around your application OLTP database in that little kind of space. It's about how do we pull in different types of data and manage them effectively. So we're going to pull in data sources from devices, from open government data sets, from social providers, structured data, unstructured data, logging data. How do we take all of this data, bring it into our systems, and make sense of it? And as the numbers of and the differences become more apparent of the types of data, we're going to need to apply different patterns if we have any hope of managing this influx of data. So that's the challenge, I guess, to start with. The other major consideration is what's changed when we move to the cloud. And we can kind of group these into two major changes. The first one is around the physical hardware. right? So on-premise, I build to spec my application servers and my database servers. Chances are they're still actually plugged into the same physical switch. I have a big, fast SAN that I've spent a whole bunch of money on and performs brilliantly. Suddenly I move into the cloud and things are quite different. My applications are going to be running in the same data center, but latency is suddenly going to be an issue. The disk speeds are probably going to be a little bit less performant than what I'm used to. And the servicing is going to happen, whenever Microsoft deems it appropriate, not when my IT team necessarily thinks it's appropriate. So we suddenly find ourselves in a scenario where we have high latency, slower disks, unexpected failures. So our applications and our data platforms have to be more resilient than they ever have had to be before. The other major change is how we purchase. Now, if you've been to any cloud talk in the last 5 years, you would have heard the spiel about OpEx versus CapEx. But it actually has a pretty big impact when we talk about how we buy our data service technologies. So traditionally, on-premise, there's a 3-year purchasing cycle. I go and buy my SQL Server box. I license it for 3 years. I have to estimate what capacity I'm going to need in 3 years' time, so I massively over-provision what I purchase. And once I've gone through this rigmarole of the budgeting and the purchasing process, I've spent so much money, I use SQL for everything, right? It's there, it's available, it's the easiest choice. When I move to the cloud, on the other hand, I now pay for everything per minute, per hour, per gigabyte. So every time I want to add something to my application, I get to make that decision again. Where is the best place to store it? Because wherever I store it, I'm going to get charged more. So this, as developers, gives us a whole bunch more flexibility, and it makes it all the more important that every time we look at extending our applications, that we have to kind of go through this process again and say, do I continue to shovel data into my current data source, or is it time to switch over to something that's more appropriate for the workload and the structure of the data? So the amount of data is exploding. The public challenges, the challenges of the public cloud are undeniable. There's also some considerations about Azure itself. So when Azure launched, we had cloud services, we had storage, and we had SQL databases. And we built amazing, fantastic, scalable, exciting apps on this platform. And then, I'm not sure when it happened, but it's definitely within the last couple of years, this happened. And suddenly it was, okay, well, I have some data, where do I put it? I have all of these different options. And this has happened across the public cloud spectrum. Amazon is exactly the same. There's been an explosion of data technologies. And some of these are really cool. So what we're going to aim to do today is think about some of the problems that the cloud presents us and look at the various solutions that we have and try and come up with some rules about when we're going to use each of them for different classes of problems. Right. Level 1, let's get started. So what does the minimal data solution look like on Azure? So I have a whole bunch of rules that I've put together for this presentation. Basically, all of them have caveats. So they're not so much rules, they're more guidelines, but I only had so much space on the slide, so we're going to stick with rules. So rule 1, if it isn't relational data, don't use a relational database. Now, you might expect me at this point to start ripping into relational data stores and go on a bit of a rant about NoSQL. Nothing could be further from the truth. Relational databases are well understood, proven technologies that are incredibly feature-rich, and chances are they will remain the bedrock of business applications moving forward. So let's start with this. Let's start talking about how we manage relational data. We have to admit, though, that with all of this feature richness that relational databases provide, it's not magic. There is a cost behind this feature richness. So all Rule 1 says is, if you don't need all of this cost, if you don't need this sophistication, if it isn't relational data, don't use a relational database. But, like I said, chances are there will be some relational data that you deal with. So, relational data on Azure. You typically have two choices. We have Azure SQL and SQL Server in a virtual machine. Now, if I was standing here 12, 18 months ago, the advice that I would have given you would be completely different. So if you haven't looked at these two technologies in a while, then it's time to take another look. 18 months ago, Azure SQL, well, good luck. It could store a lot of data, but you had no proven performance or reliable performance that you could select. So that meant SQL Server and a VM was the only choice, really, for what you would want to run your serious cloud applications on. However, things have completely flipped now. Azure SQL has delivered a fantastic platform. So that should now be your default choice for relational data stores. So they've done a whole bunch of stuff. Their SLA is better. They have some interesting replication topologies if you need high availability. They have additional features that used to be only available on-premise, like transparent data encryption and full-text search. They've closed the feature gap in terms of the query syntax that you can use compared to SQL Server on-premise. And most importantly, you can now select defined performance levels. So not only can you select how much data you want to store, you can actually say how much performance I need dedicated to my application. However, SQL Server in a virtual machine is still there. It's still available through the Azure portal. When do I use this? What are the things that I want to think about before I go down the Azure virtual machine route? Two easy ones. One, existing apps. If I have it running on SQL Server on-premise, chances are the easiest thing to do is just going to be upload that VHD to the cloud, turn it on, away you go. So lift and shift is still going to be a key scenario for SQL Server and a VM. The other key scenario is going to be the extended feature set. Right, Azure SQL provides the relational database, but if you want to do things with analysis service, reporting service, integration services, the in-memory table technology, that's still something that you're likely to need to run SQL Server and a VM for. The other things are really about control. So if you want to customize the hardware so it has, half a terabyte of RAM, or InfiniBand networking, or you want to join a domain, if you want to replicate to on-premise, if you want crazy fast network storage, you're probably still going to need to go and use Azure and a VM, SQL Server and a VM. So, relational storage, pretty simple. Azure SQL should be your first go-to option. But the thing about relational databases, and this has been true since their introduction, is that they are hard to scale, right? You can add additional resources to your relational database system, but that's about it. Effectively, the workload, because it is highly stateful, needs to run within a single system image. So that makes them quite expensive to scale too. You're going to start hitting the limits of what's possible to run in a single box, and chances are your credit card's going to run out a whole bunch sooner than what's going to be possible from your hardware vendor. So, before we go much further, it's really important to think about how we can protect our most expensive, hard-to-scale asset, and that's caching, right? So this is where Rule 2 comes from. Caching isn't necessarily about performance. It's about protection. So how can we protect our database from our application? Because most applications can generate unbounded numbers of SQL queries and therefore kill your database as quickly as you like. So let's talk about caching. But before we talk about this, and before we go into the rest of today's slides about all the different patterns we can apply to make our lives easier when managing data in the cloud, we have to have a really serious discussion about cost. And the rule here, hardware is cheap, developers are expensive, sums it up pretty well, right? We can talk about a whole bunch of different patterns for making our application scale and our data scale a lot more elegantly. However, we need to trade off, right? Maybe the easiest thing to do here is to throw more capacity in the SQL Server, right? We'll just scale it up. When my boss saw the slide, he termed it, let's kick the can down the road slide. And that's basically what we're doing here, right? So because we pay for everything by the hour, we should keep this in mind when we look at our development costs. And some of the things that I'm going to talk about today are expensive to build out, especially for existing applications. So keep this in the back of your mind before rushing off and sharding your database, for example. So back to caching, back to protecting our database. So a few simple patterns for caching. We want to look at cache aside pattern, which is that little diagram. If you can't see the diagram, don't worry, it doesn't need a diagram. The cache aside pattern is the data in the cache? No, get the data, put it in the cache for the next person. So it is just the caching pattern. Other caching patterns that are worth looking at, and one that we've been using a whole bunch recently, is the cache seeder pattern. So that is, rather than waiting for users to request data, actually put the data into the cache proactively through a web job or something, right? And that's going to avoid cache misses and avoid instances of poor performance. Where things really get interesting, and which we're going to dive into in just a moment, is around in-memory databases and how we can actually do things that are well beyond simple key-value cache approaches. So how do we do caching on Azure? Redis is the starting point. Microsoft have tried to build a cache solution on Azure twice now. Both of them have been retired. So I think Redis is probably going to be the way that we go for the foreseeable future, and it should be your default cache option. It's a great key-value cache, but it's also so much more, and we're going to look at this in a moment. So if all you're using Redis for is storing keys and values, then you're missing out a little bit. The other one that you can sometimes think about is Azure role caching. If you are using cloud services, you can dedicate some of the memory, if you have spare memory, in those cloud service roles to caching. Now, that's okay if you've got spare memory. It's also okay if you need a super low latency cache, but generally Redis is going to be the right solution for all of the problems that you have with caching. And as you'll see on basically every slide today, now that we have virtual machines, Linux, Windows, a whole bunch of different SKUs in terms of memory and CPUs and the like, deploy your own is always going to be an option worth considering as well, albeit with a pretty high tax to pay in terms of management and tuning. Right, another rule, and this kind of continues along the line of protecting our database. So if we don't need to do something synchronously, let's do it asynchronously. Let's use queues and message buffers rather than relying on the fact that every single dependency that we have will be available the whole time. When we make synchronous calls to different services, we're effectively tying our application's SLA to their SLA. And as the number of dependencies grow, this becomes problematic because you can guarantee all of their SLAs are going to be different and all of their SLAs are going to have outages at different times. So our application's SLA just kind of tanks. So where we can, let's go and use asynchronous messaging, and that's going to kind of protect some of those hard-to-scale dependencies. So the thing to remember about asynchronous messaging is it doesn't need to mean that it's slow, right? Both of these messaging options have super low latency, 10, 20, 30 millisecond latencies. So we can still do, operations asynchronously that seem, synchronous to the user. So don't rule it out just because you need to do something quickly. It gives you that escape hatch when your dependencies go down, not to take your entire application offline. So there are two options on Azure for queuing, and by now you'll probably understand where a lot of the slides kind of lead us. We're going to do a little bit of a head-to-head comparison and help make decisions about which one's best. So Azure queues, Service Bus queues, both have been around for a long time. There is extensive documentation on MSDN about when to choose which one. They are quite different. Azure queues, you get what it sounds like. It is a queue. Service Bus is a messaging platform. It does pub sub, it does filtering, it does different delivery guarantees, it does dead lettering. So how do I choose between the two? Have a look at the documentation, but check out the bonus rule. Choose the simplest thing that could possibly work. So if all you need is literally a queue, just use Azure queues. So that is kind of the minimal data platform, right? So we have a relational store, we're protecting that relational store in some kind of a meaningful way with cache, and we're going to use some asynchronous messaging where it makes sense. For our examples today, we're going to use a solution called Parts Unlimited. It's available on Microsoft's GitHub account. It's a pretty simple ASP.NET MVC e-commerce sample site. The one thing that it's got going for it is that it's entirely running on SQL Server. So what we're going to do today is kind of unpick this application a little bit and illustrate some of the techniques that we're going to talk about. So let's switch over. Superb. So let's start with relational databases. And this is pretty uninteresting, so stay with me. It's going to get more interesting as we go along. So relational databases. If we want to provision a relational database in Azure, you give it a name, you say where you want to put it, and that's basically it. The only tricky question that you need to answer is the pricing tier, or the amount of processing capacity that you want for your database. So on the low end, it's $6 a month. On the high end, it's $8,500 a month. So you want to make a good decision here. Otherwise, you might get some unexpected emails. the thing to realize, not only does the amount of processing capacity change, but also the predictability of the processing capacity changes. So at the high end, they're going to give you some performance bounds per second. On the low end, your performance bounds are going to be per hour. So on the low end, you're going to get fluctuating performance through that hour. On the high end, you're going to get predictable performance second after second. So how do we make this decision? Well, as part of the more recent updates to Azure SQL, Microsoft have supercharged a lot of the management views that are available. So this particular view, and let me see if I can zoom into this for those without superhuman eyesight. You can actually get how much of your capacity that you're using on a 15-second granularity basis. You can also get it on a 5-minute granularity basis, but you can actually get right deep in to see how much capacity you're using. And like everything in the cloud, don't pay for what you don't use. So you want to be able to adjust your database down if you find that you've over-provisioned. And the nice thing about the pricing tiers is that they are freely adjustable after you've finished your provisioning. So, for example, if you have a really heavy workload during a business day, but all your business users go home at night, then use something like Azure Automation and scale your database down overnight. It's a scalable solution that we can now, through these management views, make some smart and cost-efficient decisions about. So, continuing on our fairly boring examination of relational databases, once we've got our relational database provisioned, we get to set up the connection string, and that's about as exciting as you would expect it to be. Only a couple of things to note here when we go and set up our connection string. Because we are, in fact, accessing an external service, we do want to force encryption, right? We do really want to require that. We don't want to just assume it's going to happen by default. So that's one thing to keep in mind when you're building your connection strings. The other one is an interesting one that tripped us up recently around connection pools, right? The default connection pool for 88.net is 100 connections. If you have 3 web servers, they're going to try and create 300 connections under load, right? And if you're only using a low tier of SQL Azure, it's going to exceed all of the connections really quickly. So, like any kind of expensive, hard-to-scale resource, keep that in mind. And ensure that your application can't act as too much of a denials of service engine. Right, so that's relational databases. Let's shelve that and move on to something more interesting. And one of the things that is definitely more interesting is Redis. So let's actually take a look at this website before we get any further. So this is the Parts Unlimited website. It operates exactly as you'd expect it to. You can create an account, you can check out, you can make fake payments, you can look at products. So let's go and have a look at one page that we've applied Redis to. So this is the order history for my logged in user. Let me go in and look up an order. Right, so this is hitting the Redis cache to look up this order. I've cached this order by its ID into the cache. So how do we do something like that? Well, it's like we discussed, pretty simple. Check if the value is in the cache. And for this purpose, we're using the Stack Exchange Redis library. That's the recommended approach for interacting with Redis. If the value is not in the cache, get the value, and then put it in the cache for the next person. Pretty simple pattern. The only thing you need to decide is the serialization format. I'm using JSON because that was the easiest thing and the closest serializer that I had on hand. It's probably not the most efficient serializer, but for my purposes, it does pretty nicely. So, very simple pattern. You've been able to do this on all of the Microsoft caching platforms. Key value stores, that's it. The other part to this page is an order search. So I can set the date range, and I can check the sort order. I can press search, and I get my results set back. What's interesting about this is that search and the ordering is all happening within the Redis cache. It's not had to hit the database again. So this isn't designed to be a masterclass on Redis. All this is designed to do is to whet your appetite to go to the other Redis sessions and take advantage of all the cool features that Redis provides that you're probably paying for anyway. So how does this look from a code perspective? So rather than just putting a key value pair in, we can actually treat the records as individual items in a set. So when I go to the database, or the Redis cache, sorry, let me just scroll across so you can see the full set of functions here. Cool, so not only do I pass my usual cache key like normal, but I can provide a range. So I've indexed all of my orders by their date. I can provide a range, and I can provide a sort order. We built a service recently on Azure Mobile Services, so we could take advantage of their offline sync. And when we tried to scale it, what we found is because offline sync does a diff between what you currently have on your client device and what's new, every request that we were getting was different, right? Because it all depended on the last time the client was synced. So it became really hard to cache those responses because everyone was different. So instead, we took an approach like this, where we put the whole data set into the cache, and then we could allow the clients to make intelligent queries against that based on just the amount of data that they required for their particular query. And the caching pattern is pretty similar here. If the data doesn't exist, we just load it up as a set of data rather than just a key value pair. So, key value pair caching, sets, another cool part of Redis. The third really cool thing with Redis that I want to show you is around how to get an even bigger performance bump. And I think it's... yeah, it's this one. So if we go back to the website, you'll notice that on the homepage there are a couple of product queries that we need to make. The first one is recently arrived, and the other one is top selling. The fastest Redis call you can possibly make is a call that you don't make to Redis at all, right? So for these high traffic areas, we need to think about having another level of caching, which is just the in-memory cache that's available through .NET. Now, it was once said that there are two hard things in computer science: naming things, cache invalidation, and off-by-one errors. So the cache invalidation one is absolutely 100% true. So cache invalidation can also be helped by some of the cool features in Redis. So if we scroll down to the bottom here, is that we're taking advantage of Redis's pub/sub functionality, right? So I can subscribe to a message channel here. And when I receive messages from that channel, I can do actions. So here, what I've got is when I do a product update on my administrator page, it's actually going to send a message to all of my web nodes to go and refresh that data from the Redis cache. So when I receive a message on the products endpoint, on the products channel, it flushes the in-memory cache. So using this kind of a pattern and taking advantage of this particular Redis feature is going to allow me to maintain those really frequently used data sets in memory and not have to worry about going to Redis all the time. But it's also going to allow me to do cache invalidation in a way that doesn't drive me absolutely insane. There's another sample also that this is set up with. There's, under the same GitHub account, there's a Java Spring app that integrates with this particular app. And to do that, we use messaging, just plain old Azure queues. So, relational databases, pretty easy provision, just watch your performance. Redis, sure, great key value store, but can do a whole bunch more. So take a look at some of the features that it can provide you, and then use messaging where it's possible to do stuff asynchronously. Right, so that, in my opinion, forms out a pretty basic data tier on the Azure platform. Right, so we're half an hour through, and we're through the first section. That's a little concerning. We're going to have to pick up the pace. Right, so what does scale-free mean? Well, the idea here is that relational data stores typically follow this kind of scale-up pattern. We add more resources to the node. It's a highly stateful workflow. It's confined to that single system image. What's much nicer is a scale-out workflow, and this is the pattern that we recommend in the cloud. But traditionally, it's really hard to do with relational databases. And it's actually provably hard, right? So Eric Brewer came up with the CAP theorem 15 years ago. This isn't going to be a deep dive into this particular theorem, but his argument is that distributed systems cannot be consistent, available, and partition tolerant. You need to pick two. This is a pretty complex area to look into exactly how these trade-offs work, but the takeaway is we're going to have to make some sacrifices if we want to be able to scale our SQL Azure database out and not just up. The typical pattern for this is sharding. And this isn't an Azure pattern or a SQL Server pattern. It's a pretty generic pattern for databases. So we start with our database and our database schema, and we try and identify a subset of the schema that absolutely must be transactionally consistent. And in the case of the Parts Unlimited scenario, logically, this becomes the customer data set, right? So all of the information about a customer needs to be transactionally consistent. So the customer, the orders, the order details, the support cases, all of that information needs to be transactionally consistent. However, potentially, we can say that the data about all of our customers and all of our orders can be eventually consistent. So if we're willing to make a little bit of a trade-off, we can take this pattern of sharding. So the idea here is that we take that schema and we replicate it through multiple physically and logically separate databases. So that kind of gives us our scale out. And in each database, we have a subset of our data. But all the data around one customer lives in a particular database. So, for example, in this first database, we have customers A through D. The next database holds customers D through F, and so on. Obviously, this gets a little bit confusing, so we have another database or another data store that allows us to do those lookups. So if I have customer name James, I can figure out where it lives in the sharded database. Where things get a little bit more complex is this one down here. So if we think again around the Parts Unlimited scenario, while the order absolutely belongs to the customer, what about the product catalog, right? The order needs to refer to the product catalog, but the product catalog isn't something we can really split up. It needs to exist in its entirety. And that's what's referred to as a reference table. And in a sharding pattern, we generally have to replicate that table across all of the individual shards. So that becomes a little bit of a management nightmare. So this is pattern is not without cost. So if you've thought this through to the next logical step, you've just realized that we've kind of broken reporting, right? While as a customer I can log into the website, I connect to this database and all of the information about my profile is stored there. If I'm the store manager and I want to look at all of the orders for the day, suddenly I need to make a query against every single shard, every single database, and aggregate all of that data back in memory. So reporting is kind of broken, but we're working on that. So let's continue along. So Microsoft have made some pretty significant investments and progress in this area to make sharding a lot easier than it used to be. They started off with SQL Azure Federations. That didn't work out so well, so they've retired that. This is their next attempt, and it's a whole suite of tools and components that allow sharding to happen on Azure SQL. So the first one, there's a client package, a NuGet package. We're going to take a look at that in just a moment. That handles setting up the shards. It handles looking up which shard we need to use. It allows us to shard, like I described before, right? We have a set of customers A through K in one database and L through Z in another database. But it also allows us to explicitly assign customers to database. So from that software as a service scenario, this works really nicely. So I can say, my really important customer gets a database to itself. My not so important customers get to share a database. And all of those folks on the free tier, they're just lumped together in a really cheap database. The other piece of technology that sits along with this is Azure SQL Elastic Pools. So rather than allocating capacity to an individual database, we get a pool of capacity, and we can put all our databases into this pool, and that capacity can move across databases, depending on whether one is hot or one is cold, and you get a more financially efficient distribution of resources. Azure SQL Jobs, Elastic Jobs is another one. Now that we have, 100 databases to manage, Changing the password on all 100 databases is going to be kind of painful. So that's where Elastic Database Jobs comes in. So that allows us to submit a query or a SQL administration script, and that will take care of reliably running that script on every single node. And finally, this is what I referred to before. This is currently in preview, Elastic Query. So this kind of fixes the reporting scenario. So the idea here is that rather than having to connect to every single shard in my farm to get a complete view of all of the orders that have happened today, Elastic Query can do this work for me. And we'll take a look at that in action in just a moment. And the nice thing about Elastic Query is that all of those nice business tools suddenly start working again. SQL Server Management Studio, Power BI, Excel, they all can now work in this sharded way. So a whole bunch of investments, a whole bunch of improvements for building sharded data structures in Azure. So let's take a quick look at this stuff. So on your application startup, oops, let's move my cursor out. So on application startup, we connect to the shard map. That's that database that has all, well, thank you. It's going to be much easier to follow now. So on application startup, we connect to the shard map. That's the database that has all the mappings between my customer name, for example, and where it lives in my shard set. So that's a one-off. We go and do that. We look up where the information lives. Once we have that information, we can either create new shards or start using those shards. Typically, creating new shards is going to be an administrative operation, right? When one of them gets full, that's when we want to go and split them up. So this is kind of more for bootstrapping purposes more than anything else. What is kind of cool, though, is that they have built their samples and their helper code in a way that does actually support Entity Framework. There are a couple of gotchas here, but you can use your existing Entity Framework data context with this new sharded pattern. So let's look at what is involved with getting my Entity Framework data context into this new world of sharding. And the really nice answer is not much at all. So I can no longer just leave Entity Framework to its own devices because it's not smart enough anymore to figure out what its connection string is, right? It doesn't know which shard my customer's data is going to live in. So instead, I'm going to have to help it out. I'm going to need to give it a connection string before it can go in and make its connections. But that's literally the only change I had to make to my Entity Framework data context. Take a look at this. And as you can imagine, figuring that out isn't particularly difficult. So I go and take a look at what the current logged in user is, right? Because the sharding is based on users, so it's important for me to know which user it is. I grab their name. I happen to run a hash over it, so I get some uniform distribution across my shards, but that's an optional step. And then I can use the shard map, which I initialized earlier, to go and figure out what the connection string looks like for this particular user. It's pretty straightforward. Where things get really tricky is when I want to do operations across shards, right? That whole reporting scenario, that's where things get tricky. They give you a little bit of support for this. So let's go and take a look at this one. So here, this is a class that goes and finds a specific order based on its ID, right? And because we don't know who the customer is, we don't know what database to look in. So this is where things get a little bit tricky. So in this case, we're using a class that they've provided called multi-shard connection, and that's actually going to go and run this query across all of the different shards for us. So it helps us a little bit, but it's still not quite as nice as what we used to have with Entity Framework. So Elastic databases make it much easier to shard, but be very aware when you go outside your nice individual little shard or you want to do queries across them, things get a little bit more involved. So once we have our shards, let's just take a quick look. Here we go. So we'll put all our shards into an Elastic database pool. I've chosen the cheapest one because I'm running on MSDN credits, but even with this, I think it's a couple $100 a month, and I can put in up to 200 basic, i.e. very small databases into this pool. I can remove databases from the pool, I can add them into the pool. Once it's set up, it's pretty flexible. It also has integration with the Elastic Job Service that I talked about before. So if I do want to run my queries over the entire pool, I just need to provide some credentials, upload my script, click go, and it'll handle all of the reliable execution of that script across my shard set. And then finally, I have this query here. So if I look at the query itself, select star from orders, this is an example of the Elastic Query functionality. That looks like just a normal query, right? But when I look at the results, I'm actually pulling back results from both shards, right? So administrator sits in one shard, my user account sits in the other shard. So this is pretty simple to set up. We have to set up some credentials, and then we just define what's referred to as an external table. So we redefine the table in this query node, and then that allows us to do queries across our entire shard set. So again, not intended to be a deep dive into the Elastic database technologies, but this is the next step to take. Once you kind of hit those limits, either in terms of cost or in terms of performance with your relational database, the next step is to start to look at sharding, and it's important to be aware of all of these cool investments Microsoft have been making into making this a whole bunch easier. Right, so let's go beyond relational now, and we come back to rule one. If it's not relational data, don't use relational databases. But in this case, we're going to start looking at data that is in fact not relational and that we shouldn't use relational databases for. So let's go and take a look at what we have here. So when we started and we talked about some of the advantages of the public cloud, one of those key advantages is that you no longer have to buy all of your capacity up front. You are free to make purchasing decisions as you go, and as the nature of the data changes, we can start making decisions about what the best persistence mechanism is, depending on the data or depending on the workload. And when we think about generic storage options on Azure, we've covered pretty thoroughly now SQL Server and a VM and SQL database. We can now start talking about some of the other generic storage options, being blobs, tables, and the newcomer, DocumentDB. So, blobs and files, this is pretty simple, right? If you've got static content, whether it be images or videos, backups, scripts, whatever you have, best to serve this from somewhere that's not your primary application, right? Get that kind of generic static content distribution out of your application and onto something that's designed for it, like Azure Blobs. This is a hugely feature-rich platform. It's incredibly scalable. You can easily supercharge it if you need CDN caching. It should be your go-to choice for any kind of static content. The other one in the family is Azure Files, and Azure Files actually gives you an SMB share, so a more traditional Windows file share. The idea here is that this is a really great solution if you already have an application that relies on an SMB file share, right? It just makes lifting it from on-premise into the cloud that much easier. Or potentially you've got a whole bunch of VMs in the cloud and you want to share some data around. But ultimately, it's confined to a few specific scenarios. It's not kind of your general purpose go-to default option that Azure Blob Storage would be. Moving along now, kind of venturing into that NoSQL space. The first NoSQL stop, of course, key value storage. So highly sophisticated, persistent dictionaries, to put it another way. Azure Tables, I think, is a really underrated part of the Azure platform. When Adobe got hacked a couple of years ago, an enterprising developer loaded up all of the hacked accounts into Azure Table Storage. And I think there were 130 odd million. He was getting inserts of around 23,000 records a second. Compare that to the top-end SQL boxes on Azure, which will guarantee 700-800 transactions per second. Now, transactions and inserts are not directly comparable, but this is an enormously scalable and enormously fast platform. Continuing along, looking at that hacked Adobe story, When they then went to look up some of these records, they were getting response times as low as 4 milliseconds. So this thing is crazy scalable, and it all starts around and all sits around the petition key, right? So every key that you give your record has a petition key, and every different petition key theoretically can actually live on a separate piece of physical hardware in the Azure Data Center. Obviously, there are physical limits to that, but it allows for an amazing scale-out story. The problem with that, of course, is that if you want to query on something that's not the petition key, and then you end up doing a table scan across, theoretically, infinite numbers of pieces of hardware. So when you go into table storage, if you actually have a legitimate key value store scenario, it's a fantastic piece of technology. If you want to start doing queries, like you would be used to in a relational database store, this is going to drive you insane. If you want a more mature or more sophisticated key value store, HBase is a great example. It's available as part of HD Insight. It scales crazy big, billions of rows, millions of columns. What's important, though, to think about before you make this hop to HBase is that I think even a small HBase cluster is in the vicinity of 18, 20 CPU cores. So it's expensive. And if all you're doing is writing data, like maybe you want to use it for log output, those CPU cores are going to be doing basically nothing. So before you leap into HBase or something, make sure that you actually have some legitimate query scenarios that are actually going to push all of this capacity and use it, and so you get value for money. If you just want a place to dump information, there are better choices. You can always load up that information into HBase later on if you need to. Continue along our journey towards NoSQL. The next stop, document databases. So this is kind of that traditional non-relational storage type, right? So it's highly hierarchical data, complex hierarchical data. The schema is not necessarily known up front. Great example of this is in the product catalog for the Parts Unlimited scenario, right? Every type of part is going to have different types of metadata. That metadata can be hierarchical. You're going to get details about different properties. So it makes a great choice to put that kind of information in DocumentDB. The one thing to be aware of with DocumentDB is that they launched with the minimum viable product last year, and they're continuing to add features based on customer demand, which is the best way of building software that you can possibly imagine. However, it does mean some features that you might be used to in the relational SQL land might not be available. Great example of this, server-side ordering came in July, right? So before you jump into before you jump into DocumentDB, do a quick look at what kind of features that you might be expecting and make sure that it supports it. Things like paging still can be a little complex. When DocumentDB doesn't have the feature set that you want, go and have a look at Mongo. Again, it's available as a service through the marketplace. This is kind of the industry standard option for document databases. It's going to be very interesting to see where these two go over the next 12 months because DocumentDB already has some features that would be insanely awesome if they were in Mongo. So, DocumentDB has great support for indexing. It has great support for transactions. So it's a very competitive market. So keep an eye on both of them. So I told my boss that I was going to talk about Service Fabric. And he said, no, don't talk about Service Fabric. And he said, if you need Service Fabric, you'll already know about Service Fabric. So that kind of begs the question, how do you find out about it in the first place? But we'll put that one to one side. All I will say about Service Fabric, and Orleans, I guess, as well, is that there are a class of workloads that are just going to be basically impossible to build on any kind of storage technology like DocumentDB or SQL. And these class of workloads are those really highly stateful workflows. A great example of this is a multiplayer game, right? We have a whole bunch of people connecting. There's a whole bunch of state going on. The approach that Microsoft have used in both Service Fabric and Orleans is to actually keep that state in memory and replicate that state in memory so it's redundant and protected, but keep it in memory so the data is actually in with the application tier. So if you write kinds of applications that have that really highly stateful workflow, then absolutely, let's go and have a chat about Service Fabric and Orleans because they're really cool technologies. But if you're just building websites, probably going to be overkill. And a lot of the technologies that we've already talked about are going to be the right choice. There's also a bunch of services that are worth considering. There are certain types of data problems that are going to be best served by specific customized platforms. great example of this is Azure Search, right? On-premise, I had my SQL Server database. I had plenty of capacity. It was just sitting there begging to be used. I might as well use it for search too. In the cloud world, you're going to get a much better bang for your buck if you use a service that's designed specifically for this scenario. Application Insights is very similar. Sure, I could dump all of my logging data into my database, but performance is just going to be horrible. So pick a solution that provides a tuned storage experience. And then, this is kind of the last time I mention this, but deploy your own is always an option. Recognize that there are actually gaps in the platform. Right? So if you want a super low latency in-memory messaging solution, you may have to look outside the platform. If you want, to use Elasticsearch for processing log data in bulk, then maybe the tuning model that Azure Search has adopted might not be the right one. So keep this as an option, but realize that you are going to pay in blood, sweat, and tears in the amount of management and tuning that you're going to need to do to get these things up and running, and also run them in a way that's highly available, as is required in a public cloud platform. So that demo that I was going to do wasn't particularly interesting, and given the time, I think we'll just keep plowing on and talk about more cool stuff. So, big data. Big data, as the name would suggest, is quite a broad field. What I want to talk to you about today is how do we process big data in a near real-time kind of a way, right? So how do we get business insight out of our data streams without having to dump them all into a big database and query it out on demand? And this is kind of a typical big data workflow on an Azure platform. We have a whole bunch of sources that are generating data. Sometimes we aggregate that data up because the devices may not have the security or the computational requirements to directly connect to the cloud. And this is where we're going to start our discussion. We're going to talk about how we get data into the cloud, how do we process data, and how do we store data. So, getting data into the cloud. Let's talk about, just briefly, what we mean about before we go in and launch ourselves into these kinds of technologies. When we talked about the two queuing technologies before, they're going to do thousands of messages per second, right? They're going to do that very nicely. The programming model is well understood. They're reliable. They're robust technologies, easy to adopt. So if you're doing 10, 20, 30 messages a second, going down this route might be a little bit overkill. But the sweet spot is when we get beyond that kind of limit. Event Hubs, the latest stats I could find was processing in the vicinity of over 30 billion messages a day. Unlike a lot of the existing queuing platforms, are really designed from the get-go to scale out massively and support massive load. So the soft limits in the portal, I think, restrict you to in the neighborhood of around 20 megabytes of throughput per second. So big scale. It's designed with low latency. It's designed with a whole bunch of protocol support. If you're doing big data ingestion into the cloud from devices and the like, this should be your default choice. You could also look at Kafka, which is an Apache product, is also a recognized industry standard for ingesting data. However, you do kind of have to manage this a little bit yourself. So if Event Hubs works for you, it's a great option. So I've got my data in. So Event Hubs, it's not strictly a queue. You kind of have to maintain a little bit of state to figure out which messages you've processed, which messages you haven't. But once you've got your data into the cloud, you've got it into that buffer, then you can process it through one of these different technologies. Again, this isn't going to be a masterclass about these different technologies. What it is going to say is that these technologies are really different. They all can do similar types of things, but the way that you work with them is completely different. So the first one that we're going to talk about, so this is actually the nuts and bolts of looking at the stream and calculating some statistics on that stream. The first thing that we're going to look at is stream analytics. This is a crazy good place to start. So, prices are, I think something like $20 a month to start with, and it scales up obviously, but, super simple to start. You write your queries in a language that is actually quite similar to SQL, right? So it's a familiar development environment. It's got a whole bunch of adapters, right? So you can connect it to Event Hubs, you can connect it to Power BI, connect it to SQL. So you can get up and running on analyzing your data stream super quickly and at a really reasonable price. However, what you see is what you get with stream analytics. There's no massive extensibility model with this. So we have to make sure that, again, we choose the right technology for the kinds of things that we're trying to achieve with our processing. So where do we go from here? Industry standard is Storm, again, available on Azure with HD Insight. Completely different programming model. So here we're going to be writing classes, we're going to be implementing interfaces, implementing methods, and we're going to take a look at this time allow. So very different model, but incredibly scalable. And again, with like anything Hadoop, starts at around 1820 cores. So you better be processing data at volume before you go down this path. Otherwise, you're going to be just throwing money away. And if you're in the business of throwing money away, we should definitely catch up afterwards because I have some ideas. Other options, we can look at Spark. This is what the new kids on the block are looking at. It's just arrived in preview on Azure. It's an in-memory processing engine. They have streaming extensions, which allow you to do kind of real-time processing in micro batches. But the other one to look at potentially is Service Fabric. It's not really designed as a really high-volume data ingest and analysis engine. But if your workflow, again, is highly stateful, potentially it's something to consider. And then finally, once you've done all your data processing, obviously you have to dump it somewhere. You don't want to throw it away because, like we know, it's very difficult to go and reconstruct that data later on. A whole bunch of the technologies that we've already talked about today make great places to dump the data. However, two technologies are worth mentioning that we haven't talked about already. The first one, Azure Data Lake, was announced, I think, at Build. Currently in preview, and it seeks to resolve some of the problems that we have today with storage accounts. So storage accounts have a whole bunch of limits in terms of throughput and capacity and number of different objects. The idea around Data Lake is that it just removes all of these limitations and you get this big, theoretically infinite pool of data to put in. So when you're looking at these kinds of solutions, you've got a lot of data. You've got kind of terabyte, petabyte level data needs. And eventually it just exposes all of this data through an HDFS endpoint, so the Hadoop file system. So if you're going to be putting data in here, chances are you're going to be working with Hadoop with it. Otherwise, it's going to be a bit of a pain. But if you do have petabytes of data, then Hadoop's a really good choice for working with it because most of the other technologies are going to fall over. The other really cool technology that I think also announced in the build timeframe was Azure Data Warehouse. And this is a super scalable version of Azure SQL. And it has a really cool party trick in that you can load all of your enormous data sets into the service and then turn the data warehouse off and stop paying for all of the compute resources. You just pay for your storage. And then when month-end processing comes around again and you have to do all your reports, you scale it back up, you turn all the capacity on, and you get all the fantastic performance that it can offer. So obviously, if Data Lake is around HDFS, then it's for Hadoop. For Data Warehouse, it's going to be around SQL, so it's going to be more focused on SQL. Now, the lines between these are not strict. As we get closer to public release, I'm sure there's going to be some discussions around how these work together. But for the moment, they're kind of the two ones that we haven't talked about and are important to consider when we're storing data. Okay, so unfortunately, I'm not going to be able to show you my... actually, let's just go. Let's do a couple more minutes. Just bear with me. That one. So let's just take a really brief look at the stream analytics piece, because this kind of reinforces what I was saying about how easy it is to set up. So inputs, you point it at your event hub. Outputs, you can point it at, it's not what I wanted to do at all. Outputs, you can put it at a whole bunch of different places. You can also point it back into queued storage mechanisms. So if you think about building an event-driven architecture, right? So you get the stream in, it generates some events. Those events, they'll go into another data source and then get processed through that stream. And because they're all buffered storage places, if one slows down or one speeds up, we're not going to have any problems. And then lastly, the query, pretty simple, very SQL-like. It's not SQL, but here we're just generating over a 1 minute window what the average temperature from the data stream is. Super simple to get started with. Storm, on the other hand, and I won't get into massive detail here, but let's take a look at an example of a Storm Bolt. This one's a good one. It's classes, right? This is very much what you would be familiar with as a .NET developer, right? You're taking some data in, you're doing some activities on it, and you're spitting it back out. And the idea with Storm is that we have a whole bunch of classes like this so we can scale them out onto different nodes. So each bolt does just a little bit of processing and pushes it to another bolt. So in the interest of time, I will leave things there and switch back to wrap things up. Appreciate you staying with me for an extra minute. Right, so final rule to remember. Something's always broken. We're going to be taking a whole bunch of dependencies on all of these really cool technologies that are going to allow us to do amazing things with our applications, but something's always broken. So if you start adapting and adopting all of these kinds of technologies to your application and you don't take the right steps within the application to handle these failures, your application is going to fail just as quickly as these other technologies. So there is a fantastic resource called the Cloud Patterns Cloud Data Patterns on MSDN, and it talks about a whole bunch of different patterns you need to think about when you're working at scale in Azure. It talks about how you retry, and this becomes a whole bunch simpler because most of the Microsoft libraries that are currently out there now support some kind of built-in retry. Storage library does, DocumentDB library does, Entity Framework does. So for all of those little micro outages when they've decided to load balance or something, if you configure your software and your packages correctly, it's just going to take care of that for you. Circuit breaker pattern is the next step up. So figuring out how you can back off elegantly when a serious failure happens and then reestablish that connection in time. And then obviously data centers do fail over or collapse entirely. So make sure that you can handle those critical failures too. Other patterns: prefer chunky communication over chatty communication, prefer optimistic concurrency, ensure that you leave yourself sufficient flexibility to go in and completely replace your storage layer when you eventually break it. Make sure that you don't hold out any hope for a distributed transaction manager anytime soon. Put in the right kinds of technology to be able to roll that back without relying on that. So, few parting thoughts, and thank you for coming along today. Inevitably, when you're building applications in the cloud, using more than one storage technology is going to be the right choice. So look at the different options that you have out there and pick the ones that make the most sense. Make sure that you keep in mind, though, that developers are expensive. And before you go in and follow all of these patterns, have a really serious discussion. Is it just going to be easier to put a bit more capacity into my SQL Server, or do I want to spend the next 4 weeks writing code to follow some of these patterns? And the last one, something's always broken. Design for failure. Expect failure in everything that you do. And you're going to get far less phone calls in the middle of the night about your cloud apps than you otherwise would have. Right. And that's me all done. These are some of the masterclasses I talked about. If you're really interested in Redis, go along to that one. Service Bus and Event Hubs there. Lots of great sessions still to come. So thank you very much, and enjoy the rest of the conference.